If a steel girder in a skyscraper is found to be weak or flexible, engineers can usually strengthen it. If a load-bearing column is inadequate, they can introduce intermediate supports or add reinforcement. The superstructure, everything built above ground level, can be fixed, but the elements buried beneath the earth offer no such second chances. When the foundation of a building yields and ruptures, little can be done to improve the situation. The entire structure simply fails. This creates a strict, unforgiving boundary in architecture, the superstructure above and the substructure below. The foundation is the lowest load-bearing artificial arrangement of a building. Whether it relies on concrete blocks, piles, rafts, or grillages, its mechanical job is to transmit the total dead weight of the structure directly into the soil. Because of its inaccessible location beneath the earth and the immense burden it carries, the foundation demands absolute perfection in its design. It is a zero-tolerance zone. To achieve that perfection, engineers rely on a vast matrix of geotechnical data before a single yard of concrete is ever poured. The diagnostic process begins with site exploration to acquire a clear picture of the underlying geology. This physical investigation allows them to fix the exact value of the soil's safe bearing capacity. From there, the data dictates the required structural solutions. Engineers must decide between shallow or deep foundations, account for the intense vibrations of machine foundations, or deploy highly specific countermeasures for volatile geologies like black cotton soil. Every decision is weighed against the potential causes of failure. Navigating this precise network of geological risk allows engineers to design the invisible architecture required to safely anchor millions of tons of material into an unpredictable earth. At the very bottom of the structure, where the concrete meets the earth, the physical transfer of dead and live loads takes place. This flowchart traces the building's weight. The foundation is the mechanical interface, transmitting loads from the roof and columns into the earth. Its first purpose is distributing the weight over a massively expanded horizontal area, preventing the structure from overtaxing the soil beneath the base. The second purpose is to load the substratum evenly. If different sections of a building settle at different rates, it results in dangerous cracking. Even loading across the footprint protects the integrity of the masonry. Controlling the kinetic flow and dispersal of these forces provides the primary defense against structural rupture. The third purpose is highly practical. The foundation establishes a mathematically flat and perfectly level surface, which is essential for all subsequent building operations to succeed. Finally, the foundation anchors the building deep into the ground. When intense lateral pressures, like wind or heavy atmospheric action, hit the superstructure, the energy travels down the columns and is absorbed by the buried concrete mass. Without this deep subterranean anchor, a tall building acts like a massive sail, leaving its center of gravity dangerously vulnerable to shifting laterally. Distribute the load, evenly apply the pressure, level the surface, and prevent overturning. These four functions form the strict operating baseline for a structure's survival. Before engineers can deploy these solutions, they have to physically breach the surface to ascertain the exact nature of the subsoil strata. This diagram illustrates a test pit. Sinking a vertical shaft like this allows inspectors to directly examine the layered soil profile. Here, the readings show a vertical descent through clay and sandy clay, eventually hitting a firm bed of gravel at 250 centimeters. When a hard, reliable stratum is found immediately near the surface, standard, economical shallow foundations can be used to distribute the building's weight. But some geology requires aggressive countermeasures. This drawing details a foundation in black cotton soil, a volatile layer that shrinks and swells. To prevent the earth from tearing the concrete, engineers fill wider trenches with granular material, seen here as sand filling, isolating the structure entirely. Ultimately, the composition of the earth determines the exact engineering countermeasure required to hold the building in place. Below the concrete footings and below the sand trenches, the downward trajectory of the building's weight reaches its end. The weight of millions of tons of steel and glass ultimately meets the resistance of the hard strata bedrock. The bedrock holds firm under the weight, reaching a state of structural equilibrium. Gravity's descent is finally arrested. Every foundation exists in a state of permanent active engagement with the earth, holding the structure in balance against the constant pull of gravity. When we pull back to the surface, we see the skyline as the visible result of a massive engineered subterranean network. Every tower and high-rise depends on these invisible roots stretching deep into the soil. But this raises a problem. How does humanity build when the surface soils possess zero bearing capacity and the hard strata is buried impossibly deep? To build our tallest structures in the most difficult terrain, engineers must abandon the shallow trenches and push into the extreme realm of deep foundations.